shown this was first shown for the Andromeda Galaxy. Edwin Hubble showed that the Andromeda Galaxy was actually made of stars that were extremely far away and that it was outside of our own galaxy. So this was a big finding because, in principle, there could be infinitely many galaxies. We're not in a particularly special place of the universe. And in particular, if the universe is infinitely large and infinitely old, what you would see is that the sky is completely filled with starlight. So you can imagine looking anywhere in the sky, and if you look far enough, you'll eventually run into a star, and given enough time, that star's light will reach you. So the sky would just be uniformly bright with starlight. But that's not what we see, obviously. So that means a couple of things. It means that the universe has to be either not infinitely big or not infinitely old. And as it turns out, as far as we know, the universe is infinitely big, but we're pretty sure that it is not infinitely old. And in particular, there was some starting point to the universe, which is the Big Bang, which I'll talk about later on in the talk as well. So the next kind of big observation that led to our current understanding of the universe is that there is a lot of dark matter. So there were some early hints of this, also around 100 years ago. But the turning point where people really started to believe this was in the 1970s with work done by Vera Rubin. She was also very well known for being one of the first women astronomers to do these things. She's very famous in cosmology. But what she did in the 1970s was she observed spiral galaxies. So our own galaxy is a spiral galaxy. So she was looking around at other galaxies similar to our own. And what she did was she started at the center of the galaxy and went outwards. And as she went outwards, she measured how fast things are moving around the spiral. And the key idea here is that if you have more mass, things can move around faster without flying outwards. So based on the visible light that you could see in the galaxy, you have some expectation for how fast things should be moving. But she found, looking at many of these galaxies, that things are moving too fast. It was just moving too fast for the amount of visible matter that there was in the galaxies. And this measurement was so precise, so few uncertainties, that people really had to buy into the fact that there was something funky going on here that we couldn't explain. So like I said, that's kind of the turning point where people started to really believe in dark matter. And today, there are many independent probes that show that there is extra dark matter. I don't have time to talk about all of them, but here's a couple of examples on the right. We're very sure that the dark matter is real. But as far as these puzzling mysteries of cosmology go, dark matter is kind of normal. As far as we know, dark matter acts just like regular matter. We just, for whatever reason, are not able to see it. Like it's not giving off light, it's not interacting with light, but we know it's there from its gravitational effects. Okay, so that's dark matter. The next big observation is that the universe is expanding. And there's a couple of classic visualizations for this. You can think about this in 2D or you can think about it in 3D. The textbook examples are like imagine galaxies on the outside of an inflating balloon, or I don't know why raisin bread is always used for this, but you can think about galaxies as raisins in a baking raisin bread. But the key idea is that in both of these cases, while the universe is expanding, objects that are further away from each other are moving away faster. And for me, it's easier to visualize this in the balloon case. So you start with the deflated balloon, and there are galaxies that are right next to each other, and there are galaxies that are further away. And as the balloon inflates, you get to this bigger image over here. The galaxies that started closer to each other are still kind of close to each other. They're not moving apart that fast. But the galaxies that are further away from each other have covered a lot of ground. They're moving away very quickly. Again, that's the fundamental idea here. And actually, what we see is that we observe this effect in galaxies. So about 100 years ago, Edwin Hubble again, measured nearby galaxies, how far away they are, and how fast they're moving away from each other. And you find this kind of linear relation, which is exactly what you would expect, in the raisin bread case of the universe. So this supports a Big Bang scenario again. So if things are like if the universe is expanding today, you can imagine going back in time. It can't have gone backwards in time forever. It must have started at some point. So again, that is evidence for kind of a Big Bang scenario. Uh, Importantly, that is, the Big Bang happened, and the universe is still to this day expanding from that initial point. And then the last of these observations, and this is the strangest one, is that the universe is accelerating. So it's not only expanding, but it's getting faster and faster. And so a little background for this measurements, the what I told you about before, measuring the galaxies and how fast they're moving apart from each other, that's using relatively nearby galaxies. But what we wanted to do with this measurements is measure how the expansion is changing over time. And to do that, you need to look at things that are very far away. So galaxies become too faint, and you need things that are extremely bright to be able to make this measurement. And luckily, we have something that accomplishes this. Supernovae are exploding stars, and there's a particular type of supernova called a type 1A supernova. And when these go off, like there are trillions and trillions of stars in a galaxy. When one of these supernovae goes off in a galaxy, it for a period of time is brighter than the entire galaxy. So a lot of energy is released by these explosions. It's great that we haven't had one near us anytime recently. But we use these in order to see very far away into the universe. And what we can do is we can look at the brightness of these things versus the distance away from us, and we work out what we call the expansion history of the universe. And actually, back in the 90s, this was one of the science goals of the Hubble Space Telescope. This was one of their primary things that they wanted to accomplish. So what you expect is if you have a Big Bang, what you expect is that it expands outwards, but because of the gravity of all of the stuff in the universe, the expansion should actually slow down and possibly even collapse back in eventually. But when they measured the expansion history with these supernovae, what they found was that the universe is, instead of slowing down, it's actually expanding faster and faster and faster, which was extremely surprising and weird. So this work was done. The results were around 1999. These came out, and it won the 2011 Nobel Prize. And in order to explain this, there's some unknown force that's causing the universe to accelerate outwards. I guess analogously to dark matter, they called it dark energy. But dark energy is much stranger than dark matter because whereas dark matter behaves like normal matter that we can't see, nothing that we know of behaves like dark energy. There's no reason that the universe should be accelerating outwards. And you can see on the right here some quotes of concerned scientists that are puzzled by this mystery of dark energy. And just to kind of illustrate this more concretely, the universe accelerating outwards is kind of like if you threw a ball in the air and instead of slowing down under gravity, it just shot upwards into the air, accelerating upwards. So there's something very strange going on here. That's the story behind dark energy. These are kind of the components, the observations that led to our current understanding of the universe, and it leaves us with some big questions, like what exactly is dark matter? What exactly is dark energy? How will the universe end? And there are a lot more questions, but I'll answer these a little bit later on in the talk. So that's part one. That's kind of like the overview of all the terminology and the pieces that we know of. And I guess if people have questions, it would be a great time to take a break for those right now. Maybe I did a great job at explaining it, and there are no questions.
I don't see anything currently.
Okay,
Oh,
I see the comment. Thank you very much.
okay.
Okay, so if that in that case, we'll jump right into part two, which is again the observables that we use to learn about the universe. If you ask how we can explore the universe, I mean, we're still trying to get to Mars. It would be great if we could go to other galaxies, but unfortunately, we can't do that right now. So we have to use telescopes to explore the universe. And this part is about like what we're looking at, how we learn about the universe. So again, going back to this picture, so there are many epochs of the universe, and we can actually see many of these using telescopes. I'm going to focus on a couple of them in this talk that I think are cool and that I hope you remember. The first of these is the cosmic microwave background, and the second of them is galaxy clustering. So the how galaxies are distributed as we see them today. So let's talk about those both. So the cosmic microwave background. has this crazy, confusing name. This was explained very badly to me when I first learned about it. Here's a picture of the cosmic microwave background, and I remember when I learned about it for the first time, I was thinking, what does this actually mean? What am I looking at? So I'll try to explain it better than it was explained to me. Basically, if you could see microwaves, and keep in mind that microwaves are just a type of light, it's a slightly less energetic light than the visible light that we see with our eyes. But if you could see microwaves, the sky would always be glowing, even at night. There would always be light coming from the sky. So that's cool, but the really interesting part is that the light is not coming from anything nearby. This light is traveling to you from the Big Bang. It's been traveling for 14 billion years, and it hasn't hit anything until it hits your eyeballs or our detectors on Earth. So that's pretty crazy. And there's this quote from David Tong that I'll paraphrase as scientists, we underplayed our hand by giving this a really confusing name, instead of jumping around saying that we've taken a picture of the Big Bang, which is really what this is. So here is said picture of the Big Bang. Now that you know more what you're looking at, let's take a step back for a second. So here is the cosmic microwave background, this epoch right here. Today, the sky is filled with stars and galaxies and things like that, and structures. But if you go before the cosmic microwave background, all of this stuff, the universe was just a uniform hot plasma. There were no stars, there were no structures. All of the light and matter were coupled together into like a soup, basically. So when you look at the CMB, what you're looking at is the plasma. And in particular, it's extremely uniform. So all of these little red and blue spots that you see in the CMB are magnified 100,000 times. There's almost no variation in this plasma. But the hot and cold spots are due to these tiny little perturbations in the plasma, which eventually, as the universe cooled and developed, became the structures that we see today, which I think, is pretty cool. So the CMB, I hope I've convinced you, is great. It's very interesting, and in fact, it was kind of what confirmed the Big Bang model. We can do mathematical calculations with it, and given our model of the universe, it means that the universe was originally this hot, dense plasma, and the photons that we see in the CMB today still carry these signatures. And famously, the CMB was an accidental discovery. So here's Penzias and Wilson at Bell Labs. They were just trying to make a very precise radio antenna. And what they found was that no matter which direction they pointed their antenna, they got this flat like noise, like a hiss in their antenna. And this is all documented. They thought it was bird poop causing the signal, so they scooped all the bird poop out of their antenna that you see there. And the signal was still there. And eventually they won the Nobel Prize for discovering the CMB. But beyond the discovery, what cemented the current cosmological model was the WMAP CMB satellite. So this telescope went into space in the early, I guess the data came in the early 2000s, and it measured the hot and cold spots in the CMB in such a way that we could precisely analyze them. And what we found is that the universe started with a Big Bang, and it's precisely made of 70% dark energy, 25% dark matter, and 5% normal matter. And I'll talk a little bit about how that is arrived at later in the talk. But this is really what cemented our current cosmological model. And I should note that again, this is super recent. Like we've only had this standard cosmological model for about 20 years. So that's the CMB, which I'll come back to. But I do want to talk about galaxy clustering a little bit. So if you remember earlier when I was talking about like, zooming out and zooming out, and then we saw like the big map of galaxies, they're not randomly distributed. They have some structures when you look at them. And these structures that you see they carry the same signatures of the primordial universe that the CMB has. So if you look at it, it's kind of like a web or a sponge pattern, and this is what we call the large scale structure of the universe in cosmology. Um, so the question is, what determines the structure both in galaxies and the CMB? And there are several things that do this, but I'll give you one example. There's some crazy stuff going on here, but hopefully you can take this one away. So one thing that sets the structure in both galaxies and the CMB is called baryon acoustic oscillations. And I have a video on this. It's pretty cool. But before I start the video, I'll explain what you're seeing. So basically, if you think about the hot plasma of the early universe, like I mentioned, it's extremely uniform, but there are some points in the plasma that just by chance are a little overdense. There's a little more matter density there or energy density there. So because the universe is a plasma and like light and matter are coupled together, waves are able to expand out of these points. And those waves, this is basically right after the Big Bang, the waves travel outwards until the universe cools enough for them to freeze into place. So these waves freeze into these overdensities and they create like gravitational wells. And as the universe continues to expand and cool and develop, eventually galaxies form and they populate these wells that are left over from those waves. And today, what we can do is we can look out at the galaxies that we see. And one thing you can do is you can count pairs of galaxies as a function of how far apart they are. So this is just illustrating that measurements. And if you count enough pairs of galaxies, what you actually recover is that BAO peak, as we call it, which is the preferred separation set by those primordial waves in the early universe. So that there was a lot of explanation there, but yes. So baryon acoustic oscillations, the acoustic and acoustic oscillations actually is because they are sound waves in the primordial plasma. Just like sound travels in air, these waves traveled in the primordial plasma and seeded the structures that we see today. So again, the original imprints of this are seen in the CMB, and then galaxies, as they take a while to start developing, but they develop preferentially in the overdensities left over from these waves. So this is one of the things that we can use to constrain cosmology, and it appears in both the CMB and in galaxy clustering. Uh, oh, sorry, I see I may come back to this question in just a minute at the end of the section. But okay, so how do we actually measure cosmological parameters? So again, here's like this map of galaxies, this sponge, this web. If you modify anything in cosmology, like if you change dark energy, if you change dark matter, it creates a different web structure. And it's a different enough web structure that you can compare different theories of dark energy and dark matter to what we see in the CMB and in galaxies, and you can use this to constrain, how much of those things there are. So that's where we arrive at that's how we know that the universe is 70% dark energy and 25% dark matter. It comes from comparisons like this. Okay, so that's the end of that section. I'll take a look at this question. Um, the Friedman equations. So somebody is knowledgeable about cosmology. Um, yeah, so this is a good point. I did leave out a lot of these details in the interest of time, but uh, yeah, what we observe, let's see if I have a good slide for this. Um, I'll give a slightly quick answer now, and I'll come back to it after the next section. But so the question is, how do we know exactly what time in the universe all these things happen? Time isn't something that we directly observe. What we do observe is what's called redshifts. So as light travels in the universe, and the universe is expanding, the wavelength of the light gets stretched by the expansion and becomes redder. And we have ways of telling how much the light was stretched. So we have equations called the Friedman equations that come from general relativity. And these are how we connect the amount of redshift to like a change in time. And that's how we back into all of the times that I talked about. So correct, like the how we get from like what we observe, which is redshifts, to cosmological times, that all is connected through the Friedman equations. And when I talk about data from the telescopes, I'll come back to redshifts a little bit more. Although I don't have the Friedman equations written on a slide anywhere, unfortunately. But that is a good question. Very knowledgeable about cosmology. Uh, any other questions before I move on to part three? All right. In that case, I will talk about some of the actual telescopes on Earth and in space that we use to probe these things. And I'll start off with, like I mentioned, my own collaboration that I work in, which is called DESI, which stands for the Dark Energy Spectroscopic Instrument. Um, so this is a ground-based telescope. I know that many people at Embry-Riddle may be interested in space-based stuff, but hopefully I can convince you that telescopes on the ground are cool and interesting as well. But so DESI is located at the Mail Telescope, which is in Arizona and Kitt Peak National Observatory. You can see the Mail right here. And what DESI is doing, DESI is on the galaxy clustering side of things. It's creating the largest 3D map of galaxies that has ever been made. And actually, it has already done this, and I'll talk about that in a few slides. But if we take a peek inside of the dome here, this is what it looks like. So for a sense of scale, towards the bottom here, you can see steps and ladders. So this is really quite a big structure here. And I've been there in person, it whips around pretty fast. So it's able to look at different areas of the sky and move around quickly. And basically at the bottom here, this is where what we call our primary mirror. So light comes in from the sky and bounces off of the primary mirror and is focused into the DESI instrument right here. I'll do a zoom in now to kind of the opening to the DESI instrument. And this is what it looks like. And maybe you don't know what you're looking at, but it's actually pretty interesting. So the focal plane, as we call it, is made of 5,000 little robots. So these are each like a pencil-sized robot that's able to independently move around, and each one can target a different galaxy at the same time. So this measurement that they're doing is actually pretty time consuming historically, but automating it like this, where each little robot can target a different galaxy at once, this enables us to create kind of an order of magnitude improvements in the map of galaxies relative to what we had before. And pretty incredibly, each of these can be positioned extremely accurately, like micron precision, within a very short period of time. And what will really illustrate how cool this is I have a video of the positioners moving around. So here's again what we call the focal plane. This is where the light is being focused onto. And each of these positioners has a couple of degrees of rotational freedom where they're able to lock on precisely to a galaxy position. It's pretty cool and futuristic to see them moving around. And what they're doing is they're measuring precisely how far away that galaxy is. I'll come back to a slide on this later, but it is using redshift. So it's measuring the redshift of galaxies like I talked about before, and using the Friedmann equations, et cetera, you can back that into how far away the galaxy is. Um, okay, so that's the positioners. And like I said, DESI's creating this big map of the universe. What I'm about to show you is the largest map of galaxies ever created. Here's another video. So basically, each of these little flashes here is a tile, as we call it. This is just the focal plane looking at an area of the sky. And like I said, so the focal plane is in 2D, but each of those fibers is measuring how far away a galaxy is. So you kind of get, for each of these measurements, you get like a skewer of the universe. So you can see as you target different areas of the sky, you get a different skewer of the universe when you measure how far the galaxies are. And by doing this, like the Earth is at the center of this thing, you create a map that looks like this. The black areas we don't observe because there's too much of our own galaxy in the way. We can't see other galaxies very well through the galaxy. But that's what the map looks like. And it's definitely worth talking about some of DESI's results. So we had our first cosmological results a few years ago, and you can tell that it was a few years ago because of this quote. But basically, Adam Rees, who was one of the original people who discovered dark energy in the first place, he shared the Nobel Prize in 2011. He saw these results and he said, as Biden would say, these results are a BFD. So let's talk about those results a little bit. This is coming from the first year BAO results. So I already, in the last part of the talk, I talked about BAO. Hopefully you remember how that works. Uh, but basically, here's the measurements. We measure BAO for all of at each of these redshifts, and we plot them here. And what you're comparing is lambda CDM, which, if you remember, stands for lambda, which is importantly a constant dark energy plus cold dark matter. So that's going to be the straight black line here. And what you're comparing it against is W naught WA CDM. This is just what we call changing dark energy. And I think that you can see by eye that our data points measured from BAO fit this changing dark energy line better than they fit the constant dark energy line. So that's really what the important finding is. And to illustrate why this is important, in cosmology, we're able to talk about the ultimate fate of the universe, and you often see plots like this. So there's a couple of like extreme endings of the universe. On the left here, you can see the Big Bang, and in this case, the universe expands and decelerates and eventually collapses back in on itself, and it ends in what we call a big crunch. And then on the right here, you can see another extreme where there's the Big Bang and the universe expands outwards and accelerates forever. And this is what we call a big freeze. And in a concept associated with the deep freeze is you may have heard of like the heat death of the universe. The heat death happens basically in a big freeze scenario, which is what you would expect if dark energy is constant, like if lambda CDM is correct. So DESI's results saying that dark energy may be changing, evolving, means that we may not actually be headed for this big freeze heat death scenario. In fact, what DESI sees is that right now dark energy is weakening a little bit. So it'll be really interesting to see, as we analyze more and more of our data, how this result holds up. If dark energy is weakening today, it really opens up the possibilities of where the universe might eventually be headed. And in fact, we did release some more cosmological results last year that basically confirmed our first year results, or at least provided more evidence for them. And this resulted in over 1,200 articles across the whole world. And you can see kind of the country distribution of the articles that were released from that. Okay, so that's all I'm going to say about DESI. Maybe it's worth like taking a pause really fast to see if people have DESI questions. Okay. In that case, I'll talk about other telescopes as well. Uh,
There is a question in the chat.
ah, is it not the one from the last parts? Oh, I see it now. Is there any timeline that 3D map data from DESI at a given date expected to maintain accuracy given the dynamic expansion of the universe? Um, so I think the question might be like at any point. Maybe I don't fully understand the question. Is it that like how long until we're able to definitively confirm these results? Is that the question here from Gabriel?
Yes, that's correct. Thank you.
Yeah, yeah. So if you're familiar with statistics, then like we often quote how surprising a result is in terms of like sigmas. So right, basically like in cosmology, if you see what's called a 5 sigma result, then that's what you take as a definite detection, basically. Right now we're at the 3 sigma range, so we're at like 3 sigma out of 5 sigma, and the question is like when will we get from 3 sigma to 5 sigma if these results are true? Hopefully, by the end of DESI, which will be in the next few years, like DESI's results will be more precise, and we'll have other, from the CMB, for example, we'll have more precise data from them. There's a possibility that, like by 2030, with the increased precision of all of these measurements, we'll reach the 5 sigma range if these results are true. But I can't say that for sure. But that's definitely like the kind of the threshold that we're looking for here. And then I see another question based on the early findings, are we headed for a decelerating or coasting universe? That one I can't say for sure because so in the case in lambda CDM, when dark energy is constant, we know very well how that universe behaves and how it will end. In this case, if we find any deviation from that, what we have to do first is figure out what dark energy is. And before we do that, we can't really say where the universe is headed. So like I said, it just kind of really opens up the possibilities of what could happen eventually. And we can't really say more for sure about that until we measure it even more precisely so that we can find out what dark energy is. Is that all cool? Okay, so if no more questions on DESI, then let's talk about other telescopes. So DESI is just one example of an experiment that's on the ground. So here's a sample of a few telescopes that are looking at large scale structure from the ground and the cosmic microwave background from the ground. Many of the CMB ones are at the South Pole, which is pretty cool. I guess it's a great place to look at the CMB. Um, but also there's many examples of these in space. So large scale structure space observatories are included over here. There's actually the Roman telescope, which is going to launch pretty soon from Florida, I think by the end of this year. And then on the CMB side, the Planck mission was recently completed, and there's another one in the works called Lightbird. But all of these telescopes, both from the ground and in space, um, they're largely using, the same probes that I already talked about. So like BAO is a big thing that all of these are looking at. And a lot of them share kind of like probes that they're using. So a question is, what are the pros and cons of going to space? So space is great for a lot of reasons. For one, there's no pesky atmosphere. I know that we love the atmosphere here on Earth, but it creates a lot of problems for observing. So in this image, you can see on the left is an image of a galaxy taken from the ground, and on the right, you can see an image of a galaxy taken from space. And this blurring is really just because of the atmosphere. So it's the same effect that you see in stars. So like if you look at a star in the sky and it's twinkling, it's not actually twinkling, that's just the atmosphere. And what happens is if you took an image of that star, for example, and you exposed for a certain amount of time, it's going to twinkle because of the atmosphere and dance around your image, and it causes this kind of blurring that you see. So it creates some challenges from Earth. And also another issue with the atmosphere is that it's not transparent to all light. So it'll both absorb light in certain wavelength ranges, and it even also emits its own light, which you have to correct for when you analyze the data. And another benefit of going to space is that you can see the full sky, which is not true from Earth, because you imagine you put a telescope somewhere on Earth, even as the Earth spins around once a year, there's going to be some region of the sky that is just below the horizon that you can't see ever. But in space, you have the ability to see the entire sky, which is great. Uh, but space observatories have their own challenges. On one hand, they're hard to service and upgrade. So famously, Hubble, when it went into the sky, when it went to space, into low Earth orbit, they found an issue with the primary mirror. It was like a very small issue, but it had to be corrected. And Hubble has had several servicing missions with astronauts installing new parts and doing repairs and things like that. And even within space, there are some orbits that you just can't do that at all. So it's very challenging to get things right from the start. And they can also be very expensive and complex. So, for example, I don't work on space telescopes, but I imagine that it would be an absolute nightmare to put an instrument like DESI into space with like 5,000 little moving parts and like so many things that could go wrong. You can't service it. Space telescopes have their own very clever ways of doing this, but it can be expensive and complex to pull these things off. And then, of course, things that are easy on Earth, like data transfer and operations, become more constrained when you're in space. So these are all challenges that you have to think about when you do a space mission, even given the benefits. Uh, okay, so I guess that's all I had on telescopes. I think that we still have a little bit of time, so I will talk about the ethics and policy questions, but I'll take another pause here in case people have more questions. All right. If not, then let's dive into ethics and policy questions. So one question, I should preface this by saying that I don't have the answers to any of these questions. These are all, issues that we'll have to think about going into the future that don't have a clear answer. But one of these questions is who gets to use the sky? So obviously the sky is a shared resource, and there are many different groups that have different interests in the sky. You have companies, you have scientists, you have governments that all have legitimate claims to sharing the sky, but kind of an illustration on the right here that shows these tensions or I guess competing interests is this is an astronomical image taken by the Dark Energy camera down in Chile. And years ago, you wouldn't have seen something like this. The streaks that you see now are coming from Starlink satellites. So you expose an image long enough, like you have to do to get these very sensitive images from the ground, and you're going to pick up streaks from like satellite arrays and things like that. So increasingly in the future, this is going to become a problem that we have to think about more in astronomy. And like I said, I don't think that there's a very clear answer for how to handle this because all of these groups have legitimate reasons to be using the sky and no one person owns it. But the question is who decides what counts as an acceptable impact on the sky? So, yeah, definitely something to think about in the future. Another question is who gets access to the data coming from these experiments? I think that this didn't used to be the case as much, but I think increasingly and certainly for experiments like DESI, the policy is that if you have a publicly funded cosmology experiment, you have to publicly release the data. So the push to public data releases is great for astronomy and the world, I think, but there are still some questions like should there be any proprietary period? Like should the scientists who are taking the data and operating the telescopes should they have any period of time where they can analyze the data themselves before releasing it out to other scientists and the public? There's no good answer for that, I don't think. And also, even if you did do that, what about data that requires significant resources to use? Like, what if the data is public, but in order to analyze the data, you need a supercomputer, which in some cases you actually do need a supercomputer to analyze these things, or just like even for storage to store the data. So the question is, should access to data include access to infrastructure? That's another tricky thing going forward. And a different question that's somewhat related is that these big collaboration cosmology experiments have really exciting results and a lot of resources to use on discoveries, but that inherently tends to concentrate participation in wealthier institutions and wealthier countries. Another open question is how to broaden participation, in these exciting discoveries going forward. And I also have here who bears the costs of discovery. So there's a lot of different angles to this question. One is that on land, the places that you want to put telescopes, the best places to put telescopes, are also sensitive places both culturally and environmentally. So Mauna Kea in Hawaii is, kind of a classic example of this, where there's been a whole lot of back and forth between observatories operating on Mauna Kea and the native Hawaiian people. And even DESI itself is also grateful to work on land in Arizona that is culturally important to the Tohono O'odham people. One question is, what's the best way to be environmental stewards of the land and also work with people that you're sharing the land with in this case? But even in space, there are also issues with sustainability and things like that. Crowding and debris is increasingly becoming a challenge that people have to think about when you're putting something in space. You can see orbital debris illustrated down here. I think this is low Earth orbit, like crowded around the Earth. And then this is probably like the graveyard orbit for geosynchronous satellites. A question going forward is what does responsible stewardship look like both on land and in space? And kind of from a different angle, uh, for who bears the cost of discovery, it can be shown, and it has been shown many times, that fundamental scientific research is a valuable investment of public money. It creates a great return on investment. But how do you balance that investment when there are competing needs for public funds? Again, I don't know if there's an answer, but certainly something that would be interesting to think about for people who are interested in the policy side of things. Okay, so that does bring us to the end. We covered a lot of stuff. I'll just leave the sections of the talk here. Hopefully you can look at each of these and remember something cool that you learned that you didn't know before. But yes, I'll end here and I'll take any final questions.
I'd like to ask a question.
Sure.
We hear so much about AI today and how it's encroaching on just about everything that we do or any field that we work in. How is that either helping or not helping in your field?
Yeah, so this is also something that we talk about a lot in science for many reasons. One being that the funding for science is now frequently being tied to AI. Like the people funding science really want AI to become a bigger part of science as well. But I think that the attitude towards AI can be mixed sometimes in science. It does make things easier, like going from an idea for a cool analysis to like a published paper. A lot of the in between parts can be automated very well with AI. It helps with a lot of the parts of that pipeline. But some people are worried that y- you know like what will a scientist's job be going forward? Like, is it just going to be like a prompt engineer for AI? People are thinking like maybe it takes the fun part out of their job. Uh, but yeah, so like everything else, I don't think that we know the full impacts of AI yet, but it's something that scientists are going to have to adjust to as well.
There seems to be a question from Ronald.
Okay, so let's see. Going back a little bit, you mentioned the universe may not be headed towards a heat or freeze death. If not complete thermal equilibrium, what would it be instead? A never-ending expansion, entropy, yes, yes, yes. So great questions. I see definitely some physics knowledge here. So basically, in the case of like lambda CDM, for example, constant dark energy, you wind up in this accelerating universe case. The reason why this is a heat death is because things expand apart so much that eventually you reach the state of maximum entropy. So like uh, basically there's no entropy left for anything interesting to happen. Like all of the life that you see around us only happens because there are little pools of lower entropy within like a higher entropy universe. So all of the laws that you are talking about with thermodynamics still hold in all of these cases, but the issue with this case is that you reach the state of maximum entropy where nothing else can happen. But if that doesn't happen, then you can wind up in any of these other scenarios where the second law of thermodynamics still holds, but you may still have like going forward into the future, you still have like the ability for like life and complex processes to happen and things like that. Hopefully that answers the question.
Well, I see no more questions. And as our dean is fond of saying, thank you all for coming, and we will give you back 11 minutes of your time. Thank you so much.
Yeah, thank you all.